Okay, so this one says sulfur dioxide, which is SO2, reacts with oxygen O2 to form sulfur trioxide as shown in the balanced equation below. So a lot of the time in stoichiometry, they'll give you balanced equations. That's fine, but if they want you to balance, just remember all the rules or how to actually balance. The key is to start with the simplest molecules, especially the ones that appear once on either side of the equation, and so on. But we do have a short video on that, on balancing. Okay, so the question continues on to say, in one such reaction, 2,450 cubic centimeter of sulfur trioxide is formed at STP. So what you need to do first is write your given data, and it looks like we have only one data that is given. That's this number here. What does it represent? Is it number of moles? Is it concentration? Is it volume? What is it?
Wait, so it's the volume.
That's the volume. Okay, looks like you were unsure.
No, so I'm just trying to figure out, so isn't volume measured in decimeters cubed or something?
Yeah, it is. That's the units that you use, but they can give you in centimeter cubed. But you need to identify the units that
Okay,
you
yeah,
have. Yeah, you need to identify which units and what actually is the variable that the unit stands for. So that's volume, cubic centimeters. They can give volume in cubic centimeters. So what you need to do is just to convert that to cubic decimeters. Okay, in stoichiometry, that's the first thing you remember. So the volume, I like to write my given data like this. I'll just put it on top of the thing that they are talking about. So that is, okay, first of all, to convert that to cubic decimeters, we need to divide by 1,000. And if you have to remember something, that is the conversion that you need to remember. So that we need to divide by 1,000, and then that will give us the answer in cubic decimeters, which is the units that we need to use. Okay, so dm3. So that's our volume, 2.45 dm3 for SO3. Okay, then 6.1, it's a definition, and we do expect definitions every time. Like every question should have a definition. You can see we have one there, we have one in the next question, and if I keep scrolling, you'll see that we have a couple of them. At least one per question, sometimes two. Okay, but I'm not sure if you already done some revision of definitions, if you have already crammed a few. How is that going?
Yeah, I'm still like learning to know it.
Okay, like or did you get the paper one definitions correct, or are there some that you forgot in the exam on
So I
Friday?
only forgot one. I only forgot the definition for resistance.
For resistance?
Yeah.
Okay, okay. Yeah, that one is not we don't see it a lot, the definition of that. I'll have to check what the question paper was about, but I doubt it was national. But anyways, if you get it, just send it to me. Okay, Avogadro's law, you go and check that. We did talk about it. This is just to train you to like look for all the other definitions that you'll need for paper 2. So don't underestimate any. They can have any in the test. For example, they like to ask the mole. They'll say define the mole in weights. That one is almost always there. Okay, but let's look at 6.2.1. They say calculate the number of moles of SO3 that formed. How are we supposed to do that one?
S- so first you're gonna get the mole of the limiting factor.
Okay, the limiting factor. And how do we do that?
So you take, but wait, so in this question they didn't give us grams.
Mm-hmm.
They didn't give us the mass. They didn't give us the volume. So
Yes.
that means we're gonna have to use the formula wait, C is equal to N over V over the mole over the volume, but then we're gonna have to like change it and say the mole is gonna be equal to concentration times volume.
Okay, so we need to use this one. Number of moles is concentration times volume. Okay, let's check if we have concentration and volume. Do we have concentration? Or is it something that we can find?
No, so we don't have it. We only have the volume.
Yeah, we only have the volume. In all the information, they only just gave the volume. So we need another plan.
Wait. So there's also the other one. N is since they said it's at STP, so that means it's a gas. So that means we can use N is equal to V over Vm.
Yes, that's brilliant. So every time it's a guess, every time it is a guess, it doesn't matter if they mention the word STP, they'll always try to do that, but it doesn't matter anyways, because every time we assume that all the guesses are at STP. Even at university, you're gonna assume that for most parts in chemistry. So every time it's a guess, every time you just see J in bracket, eh, you can see everything else here is G. You can always use that formula. You can see for SO2 and for oxygen, they don't mention STP anywhere, but you can always use that formula to find the volume or the number of moles that is related to those other gases. Does that make sense?
Yes, sir.
Yes. So once again, when you reach a question, you just go down to the formula sheet, you decide which one you're going to use, and for this case, it's going to be this one, and it's going to have a constant Vm, and that Vm is given right there. Some questions, they do ask you to use a specific Vm. They might say use Vm is equal to 20. This value is called the molar gas volume. So if they ever say use the molar gas volume as this specific number, then that way you don't have to go and pick this one out. You just use the one that they give. But if they don't specify in the question, then you are allowed to check the one that is in the information sheet, which is 22,4. Okay, so we'll do that. So this question is just to find the number of moles of something that we already know the volume of. And we know that it's a gas, so we don't have to do the limiting factor or anything. Even if we had the number of or the mass of the other things, they just specifically wants the number of moles of a specific thing, which is SO2, and we already know the volume that is produced. Okay, so in my answer, I'm gonna write the formula down. Then I'm gonna say the number of moles. I'm gonna say for which compound, and in bracket I'll say it's SO3. Therefore, now I can substitute. This way, the person who's marking can understand what I'm doing. 2,45 for V, that's the volume that was produced. Divide this by the Vm, which is 22,4 from the formula sheet. Then what do we get?
So you get 0,109 moles.
0,109
Yeah, moles.
moles. Okay, so they say it's 4 marks. I think that's a lot for this kind of question, but I'm thinking they'll mark the formula, and I don't know, maybe they'll give you 2 marks for this, and then they'll give you 1 mark for the answer, or I don't know if it's gonna be 1 mark for the number and 1 mark for the units. But usually this question goes for 3 marks. So just say expect 3 marks for that. And it's for the formula, the substitution, and the final answer. Okay, then 6.2.2, they say calculate the mass of SO2 that reacted. So SO2 is one of the reactants. I'm going to highlight it with purple. So we need to find the number, or I mean the mass of that actually reacted. How do we go about doing that?
Hold on. Just 1 second, sir.
So did you forget, or is it something you need to revise? Because I was thinking maybe it's something that you can just say.
So you can use the mole is equal to the mass over the molar mass, and then you just get the molar mass of S of sulfur dioxide.
Okay, so we can get the molar mass of sulfur dioxide. That's good, but do we know the number of moles?
Yes, sir, because we calculated it in the previous question.
Or for the previous question, it was actually the moles of SO3, the product. Now we're looking for the moles of SO2, the reactant.
Okay, so then that can't work.
Yeah. What do we usually do in stoichiometry?
So
I mean, in stoichiometry, what do we usually do to find the amount of something on the other side, or things like that? The whole chapter is built up on one thing, and that's the thing that we're looking for right now.
the mass.
Okay, let me put it this way. We know the number of moles of the product. How do we find any amount of the reactant, or if it's another product? I'm
So
not
I
sure.
can't remember.
Okay, you see, that's the thing that I was worried about. Because you definitely have to remember this. Definitely. You can't go to the exam and it can't be 2 days before the exam and you can't remember this kind of stuff, But you have to do the ratio for this. It has to be, so you compare what you're given, or what you already have the number of moles for, to what you're looking for. So I'm going to say the ratio is between SO3 and SO2, because I already know the number of moles of SO3. So I can use that. I can use the number of moles of SO3 to relate back to the number of moles of SO2, and also the number of moles of oxygen. That's why I say the whole chapter is built up on this one concept, which is the ratio. So I'm going to say under the ratio, the first thing I write is the coefficients of each. So before SO3, I have a 2. Before SO2, I have a 2. And I'm talking about these numbers here. They are called coefficients. So you go and check that, and that's the thing that you write under the compounds. Then the next thing is I'm going to write the number of moles that I am given, 0,109. I just calculated that. And I'm just going to put an N on SO2 because I'm going to find what that N is equal to. Then after that, I'm just going to cross multiply. It's 2 times N and 2 times 0,109. So I have 2 times N is equal to 2 times 0,109. And then I have to divide by 2 both sides at the end to find my N. You can just see that the 2's are going to cancel, and my number of moles for SO2, because this N is under SO2. That's the whole idea behind the ratios. I can use the ratio to find the number of moles of something else given the number of moles of the other thing. So by that, I just literally found the number of moles of SO2. And if you check under Google Classroom, we did this countless times. So I expect you guys to understand as we go on. Come on. In grade 11, you're going to have to be quick as well, because it's going to get advanced a little bit. But anyways, what I've been saying is use the recordings, and if you fail to use them for the last time, then there's nothing we can do. You have to use the recordings, please. This one is also recorded, so you will find the recording as well. But there's a lot of recordings that you have to go through for you to prepare for this exam. Okay, but anyways, we found the number of moles. That's like the first step. The second step is now to find the mass. And that's going to be easy because I just need to use the equation N is equal to M over M. And then I can just put M as the subject of the equation. So I have number of moles times molar mass. Then I can go to the periodic table to find my molar mass, because I already know the number of moles that actually reacted. Okay, so let's go to the periodic table and calculate the molar mass of sulfur dioxide. I'll just quickly identify, here's your oxygen, here's your sulfur. So what will be the molar mass of SO2?
That will be 64.
64, so that is 32 plus 2 times 16, yeah, that's 32 plus 32, 64 grams per mole. Good. Okay, so I'm just going to substitute that in.
So just a quick question, sir.
Yes.
When you're calculating like the molar mass, are you supposed to multiply by the coefficient?
Oh yes. Oh no, not the coefficient. I'm supposed to only multiply by the number that you see on the bottom. The one that comes before the coefficient is not taken into the molar mass. Like this one does not go into the molar mass, but this one on the oxygen itself does go in the molar mass.
Yes, sir.
Yes. Okay, that's a very good question. Because once you make that mistake, then there's no turning back. Everything just becomes wrong. Like the whole answer sheet just becomes wrong on stoichiometry. So very good question there. Just make sure you don't forget that. It's actually one of the things that troubled me in chemistry when I was in grade 10. Okay, but that's good. So the final answer that we get is, I get 6,98 if I round off. So 6,98 grams, and that's the mass of SO2 that actually reacted. So I can say this reacted. So that's the amount of SO2 that we used to produce the product, which is SO3. Okay, but you can tell we used the product to actually go back to identify how much of the reactant we used. So that's how stoichiometry work. You can go from reactant to product, and you can as well go from product to reactants. Okay, let's see what the last question on this say. It says, calculate the number of oxygen or O2 molecules that reacted. Okay, do you have any idea how you should do that one? We need the number of oxygen molecules that reacted. What is the first thing that we need?
So your screen stopped showing.
Yeah, actually, maybe it's the network. So what is the first thing that we need? What is the first thing we need to do? And you should have this thought process in your mind. Okay, if I'm looking for this, it means I need to do this and that first. What do we need to do first?
Aren't you supposed to use Avogadro's number to determine the number of molecules?
Yes, that's a good point. So I'll
Hence,
go
then
and write that down. We need the Avogadro's number at the end of the day because that's how we can find the number of molecules of something. That is an excellent point. So if I go and write the Avogadro's number, this is 6.2.3. Its number of moles is equal to the number of molecules over the Avogadro's number. Then, if I write or if I check my data, I'll see that I know the Avogadro's number because it's a constant, but I don't know the number of moles. So how do we work out the number of moles of oxygen?
so can you please scroll up to the question?
Yes, I think it's a little bit slow, but I am on the question now.
So you can use n wait.
So we know the equation we need to use, but the issue is we don't know the number of moles of oxygen. How do we find the number of moles of
Yes,
oxygen?
yes.
Yes.
So I was gonna say we can use n is equal to v over vm, but like I realized that was the volume was for for sulfur trioxide and not
Yeah.
oxygen.
But okay, listen to me. Let me back off a little bit. We in stoichiometry we work with number of moles. Can you repeat what I just said?
In stoichiometry, we work with number of moles.
Yes. And after we get the number of moles, we use ratios to find the number of moles of the other things. Can you also say that for me?
So please repeat what you said.
Okay, after we get the number of moles of something, we can use the ratios to get the number of moles of everything else.
So you said after we get the number of moles of something, we can use, excuse me, that number to
The
get
ratios,
the number of the ratio to get the number of
the
the
number
mole
of
of something
moles
else.
of everything else. Okay, I want that to make sense. Maybe if you say it yourself, then we just stay. So remember from the first question, they asked us to find. Okay, looks like. Can you hear me?
So just give me
Did
a second, sir. Let me
okay.
just cough.
I wonder if people will be watching the recording will be like, oh, that's funny. But it's unfortunate that you caught a flu. Maybe it's flu season because of
Yes,
when I
sir.
woke up, I was feeling like, yeah, I also have a flu. I'm gonna get some meds actually when I leave here. Maybe it is a flu season. Okay, but
Yes, sir.
yeah, can we continue now?
Yes, sir. Wait, sir. Just give me a.
Okay.
Okay, we can continue, sir.
All right. So once again, you need to find the number of moles of at least one thing. In the given data, they'll make sure that you can find the number of moles of at least one thing. And you can see that we could find the number of moles of SO3. That's the one thing that we need. After we know the number of moles of that one thing, we can use the ratios. We can use the ratios to find the number of moles of everything else in the question. That's the key. I repeat again, that's the key, or that's the main idea behind stoichiometry. You remember how we did question 6.2.2? That's exactly what we need to do for 6.2.3. So I thought maybe you'll just tell me exactly what I told you here. And you couldn't, which is a problem. Okay, but again, you need to use the ratios, and the ratios goes like this. I'll explain this again. For oxygen, you're going to use any of the molecules that you already know the number of moles of. So I'll stick with SO3. So I'm going to say, okay, we have SO3 versus oxygen. And then the next thing I write after I write that ratio is the coefficients themselves. So I go and check what is the coefficient of SO3.
So the coefficient of SO3 is 2.
Okay, and then what is the coefficient of oxygen?
So 1.
It's 1. So that's what I'm going to write there. SO2 under it, I'm going to put a 2. Under oxygen, I'm going to put a 1. Therefore, I substitute the number of moles of SO3 that I already know from the beginning of the question, and that was 0.109, and then I'm going to say is to N. Then the next thing, I cross multiply. So that 2 multiplies the N, the 1 multiplies the 0.109. Therefore, at the end of the day, I'm going to have number of moles of oxygen is equal to, this is 2 times, by the way, is equal to 1 times 0.109. Therefore, to find the number of moles of oxygen, I'm going to have to divide both sides by 2. So let's see what we get when we do that. We get 0.0545, and that's the moles of oxygen just from the ratio. That is all this stoichiometry is about. So now that we found the number of moles of oxygen, then we can use the equation to find whatever they're looking for. So step 2, because we use the ratio, and this should always be in your mind every time stoichiometry is the ratios. Then I can go to the equation and say, if I write N as the subject of the equation, I'm going to have number of moles times Avogadro's number. And if I substitute, the number of moles of oxygen is 0.0545, and the Avogadro's number is 6.02 times 10 to the power 23. You can check that value in the information sheet. Don't just guess it and maybe find that it's wrong. Okay, what is the answer that we get?
So you get 3,2809 times 10 to the power of 22.
Okay, I'm just gonna write 28 times 10 to the power of 22. Then you can just say molecules as your units, or molecules of O2. Okay, oops, I just moved the page. Let me go back. So you're gonna write molecules of O2, and that's it. Need to say O2. That is it. It's 4 marks for this kind of questions, because they'll give you 2 marks here and they'll give you 2 marks there. So you see, if you don't do the ratios, I mean, anyways, you can't solve the question before you do the ratios. So you might as well forget about the whole marks. I was gonna say you're gonna lose 2 marks, but you're gonna lose all the marks because the ratios is the key to stoichiometry. And once again, you have like a minimum of 2 questions on stoichiometry. That's why I take it so serious. And it's gonna be there in grade 11 and 12. So you need to do a lot of revision on that. But if there's anything you need to know, is you can't do stoichiometry without doing the ratios. If the first thing that pops up in your mind is not ratios, then you're not doing stoichiometry. So just quick reminder, just make sure that you are aware of that. You can see here question number 8, which will be the last question, is also on stoichiometry. Okay, this one looks to be a little bit advanced compared to the last one, but it also carries a lot of marks, 15 in total for that. So it says calcium carbonate CaCO3 reacts completely. So if they say it reacts completely, it means you don't need to worry about the limiting factor. Each of those reactants are the limiting factor. That
Yes,
is,
sir.
yeah, that is if they say it reacts. Oh, wait, okay. Before I say that, actually, I need to read the whole question. Then they say it reacts completely with excess. So they just said the other one is in excess. So there's a lot of it. In other words, the limiting factor is the one that reacted completely. The one that is in excess, we don't need to touch it because it's going to remain after the reaction. So if you are doing the ratios, you don't ever use the excess reactant. You only use the limiting reactant. And it's not a lot in grade 10 where they'll ask you to find the limiting factor. They'll only ask you to use the limiting factor to actually find the number of moles of the other things. So let's see what the question says. The excess has a concentration of 1.25 mole per decimeter cubed. So I'm just going to write that in my given data. The concentration of the phosphoric acid is 1.25 times 10 to the power, mole per decimeter cubed. I'm just going to keep that there. Maybe we'll need it in the question. Okay, I like to write given data under each molecule. Then they say the reaction is represented by the following balanced equation. Then they say the graph below, which is not drawn to scale, shows the mass of calcium carbonate as the reaction progresses. And I know a lot of learners really hate graphs and functions, but what functions do, they just give you information of whatever is going on. So if you look at this graph, what it basically says to you is that when time is 0, you can think of that as I just took my beaker, I put in my CaCO3 inside, and then as I pour in the acid, this is when my time is 0. So it's basically the start of the reaction. So in other words, at the start of the reaction, we have the mass of calcium carbonate as 25 grams. That's what the graph is telling me because it's in mass of calcium carbonate in grams. And I see that when time is 0, I start with 25 grams. That's the information I can extract from that. Therefore, I proceed with the graph. I see this point is marked. And if I say explain what that point is talking about, what can you say? What this point actually means? Is there anything you can say about it, or should I tell you what I'm thinking about?
So tell me what you're thinking about.
Okay, so this point means that you go to the time, it's 1. You go to the mass, it's 10. So what it basically says is that after 1 minute of the reaction, we used or the number of, not the number, the mass of calcium carbonate remaining is 10 grams. After 1 minute, the amount of calcium carbonate remaining in terms of mass is 10 grams. Then we can proceed with the graph. At 4 minutes, what is the amount of calcium carbonate remaining?
0.
0. That's good. So it means the reaction will actually stop at 4 minutes. Okay, that's a good observation. Then let's look at 8.1. It says determine the number of moles of calcium phosphate, which is one of the products. And this is, or they say that is formed actually after 1 minute. The amount of Ca3 into PO4 that is produced after just 1 minute. So we forget about these other points and we focus on what happens in 1 minute. And we see that the amount of calcium carbonate that actually remains is 10. This is what remains. Not what is used, but what remains. So how can we work out 8.1? 5 marks. That's like the longest question of them all.
Um, First, we have to write down what we have. So they basically tell us that in 1 minute, the thingy, there's 10 grams.
That remains.
Yes, sir.
So what do we need to say? We need to say the mass of calcium carbonate that actually reacted is equal to the mass
10
that we
grams.
start with. It's not 10 minus the mass that remains. The mass that actually remains. I'll just call it mass final. I'm not sure if this makes sense. It's like you're making tea and this is your sugar. If you find the whatever, I don't know what it's called, if initially it has 100 grams of sugar and after you make your tea it now has 80 grams of sugar, did you use 80 grams or what did you use? So before you took out some sugar it was 100 grams. After you took out some sugar it's now 80 grams. How much sugar did you actually use?
20 grams of sugar.
20. So that's what the question is about. We don't want to say the mass that we use is 10. No, that's what remains. What reacted is actually what we started with minus what remains. So in other words, we used 15 grams of CaCO3. Okay. If you
Yes,
don't get
sir.
that right, you see everything just becomes wrong if you don't get that first part right. Then I'm gonna say, okay, now that I know the number of moles of calcium carbonate that I used, I can go and find the number of moles of it. And that's always what you should do in stoichiometry. Yes, do you have a question?
No, sir. I pressed it by mistake.
Okay, no problems. So I'll say, you see, I specify in a bracket that the number of moles I'm talking about is for calcium carbonate. If you don't do that, you might lose marks because the marker might get confused. Okay, so the mass is 15. The molar mass of calcium carbonate is how much? I think calcium has a molar mass of 40. So let's just add the rest.
Yes, sir.
40 plus 12 plus 3 times 16, that's 100. So the molar mass of this is 100 grams per mole. And if we divide, we get, I think it's going to be 0.15 mole. So we just found the number of moles of calcium carbonate. because we had the mass of calcium carbonate. Once again, that's how stoichiometry works. But then we need the number of moles of the product. So we go from reactant now to product. How can we work out the number of moles of that product? What is the first thing we need to do?
So
By the way, at this point, you already have 3 marks.
yes, sir. So we can use the ratio.
Yes, exactly. Once you have, every time you have just one number of moles, once you see one number of moles, then every time think of the ratio all the time. So we need to use the ratio. Okay, so I'm gonna say the ratio between calcium carbonate and calcium phosphate is I check the coefficient of CaCO3, that's 3, and the coefficient of Ca3 into PO4, 2, that's 1. Then I know the number of moles of the first one. The second one, I'm just going to put in N. Then I cross multiply. This means that I'm going to have 3 multiplied by N. So 3 times N. And this N is the number of moles of Ca3 into PO4, 2. Then the other side is just 1 times 0, 0.15. So at the end of the day, I need to divide by 3 both sides, because I have this 3 that was multiplied to the n. So when I divide by 3 both sides, what do I get?
So you get 0.05 moles.
0.05 moles, and that's the number of moles of CaPO4 2 after 1 minute. So this is after 1 minute. The reaction doesn't complete after 1 minute, so this is just a question that actually tested if you can interpret the graph. But the key to getting everything right here was to find the number of moles that actually reacted after 1 minute, because you can easily choose 10, and that's not 10. It should be 25 minus 10, and that should be 15. So you need to think about it a little bit. So what we just did with the ratios is where your last 2 marks is going to come from. So they'll give you a mark for that, the whole ratio, and they'll give you a mark for the final answer. So in total, 5 marks. Then there's 8.3, but before that there's a statement that we have to read. It says the reaction is thereafter allowed to reach completion. So now the reaction runs all the way to the stop position, which is 4 minutes. Then the first question, 8.2, determine the number of moles of calcium carbonate that was used. You remember the first part we did in this question is we found the number of moles of calcium carbonate that was used, but only after 1 minute. Now we need the whole number of moles that was used throughout the entire reaction. So how do we do that?
So can you please help me with this one?
Can I help with?
Like, so does that basically mean like
Yes, go ahead.
So I'm still trying to think about it.
So look at the graph again. We are working with calcium carbonate. We just solved the problem whereby we were looking for the number of moles of something that was produced after 1 minute, and we established the fact that we need to first find the number of moles of calcium carbonate after 1 minute. We did that. That was the hardest question. But now the easiest question of the of like question 8, you can see it's 2 marks, is what is the whole number of moles that we used in the whole reaction if we actually reach completion. That is something that is, it should be simple really for someone that is had physics for like the whole year. It should really be simple at this point, to be honest. Because I started with 25, and after completion I end up with 0. So I can say 25 minus 0, which is just 25. Or I can just say overall I used 25. So the number of moles will come from the fact that the mass of calcium carbonate that was used in the entire reaction is 25. So I'm going to say number of moles of calcium carbonate. I'm going to suggest, I really strongly suggest that you go through the recordings. So I want us to actually stop revising, because actually there's no use if you didn't do some revision yourself, because it's just again what we did throughout the year. It's just me talking, just me giving you the answers. It doesn't work. Trust me, you have to do the work yourself. You have to make yourself understand. And maybe we should have had the lesson when you actually went through everything, and you'll be 100% sure that you can go to the exam room. Otherwise, it's not really working. I'm not sure if we are on the same page here.
Yes, sir.
Yes, unfortunately that's how physics works. You have to really think about these things, and you have to put in the work, because physics tests how you think. Unlike maths, where you just have a question that you need to solve, physics, you have to think about it before you can actually solve it. So this is the mass that I actually started with. So it's the whole mass. Let me say the whole mass that actually reacted in this reaction. Okay, maybe let me erase all this and continue with the question. So it was 2 marks, meaning that they'll give you a mark for not the equation anymore, because you already used the equation a couple of times. They'll only give a mark for the substitution and the final answer. So 2 marks for this.
Yes, sir.
Okay, the last 2 questions. Let's see. Calculate the volume of phosphoric acid that reacted with calcium carbonate after 4 minutes. After 4 minutes is just the completion of the reaction. So at this point, we don't really need to worry about the time. Let's just say, what is the volume of phosphoric acid that reacted? See, phosphoric acid is one of the reactants.
Yes, that's the second one.
Yes, that's the second one, of course. So once again, we know the number of moles of one thing. We know the number of moles of this guy. We can use the ratios to find the number of moles of the next guy. It doesn't matter if it's the reactant. It doesn't matter if it's the product. Once we have the number of moles of one thing, that's the key to solving everything. So I'm gonna say the ratio is this. I'll do 8.3 here. The ratio is between calcium carbonate, which I already know the number of moles of, versus the phosphoric acid. Then I'll check the coefficients. I think it's 3 is to 2. Yes. 3 is to 2. That's why they usually do not ask students to balance, because they know if you can't balance, then you lose all the marks on stoichiometry. That's why they balance for you, just to make sure that everything is on the same level with everyone else. Then I cross multiply. Same procedure every time. So really, there's no reason why this chapter should be hard, because it is the same procedure all the time. Then I divide by 3. Let's see what we get. Two times 0.25 is 0.5. Divide that by 3. I get 0.167.
Yes, sir.
So that's the number of moles of H3PO3 that reacted. But if you go back to the question, they're actually asking for the volume that reacted. So how do we go from this number of moles to the volume? Let me go back to the whole question. How do we go from number of moles of this acid to the volume of the acid? We need to use an equation. That's
Yes, sir.
like,
I
yes.
thought my mic was like unmuted.
Oh,
So
okay.
yeah,
So,
I was saying, I was saying, sir, since in the question they gave us concentration, we can use the formula N is equal to C over V. And yeah, we calculated the mole in the questions.
yep, that is true. What if I said, let's use this one? Because I'm looking for the volume and that one does have the volume. Would I be wrong?
No, sir.
Okay,
Wait,
why do we say it will still be correct?
sir, because we have, what's this? We can use that formula because it's a gas.
Okay, let's see if it's a gas indeed. What does AQ mean?
AQ.
The question
What
is
does
is
AQ?
it really a gas? Because I see AQ, not G. See, the one with J
Oh
is
no, so
this
it's
one
not a
here.
gas, not a gas.
Yeah. So we can't use that equation. We can never touch it unless we're dealing with a gas. So this one is not a gas. So we definitely need to use the one with the concentration. And that's the only reason why they'll give you concentration, because you have to use it in the last question. It's not really the last question, but anyways, you're not dealing with a gas, so you can't use N equals to V over Vm. All right. So I can rewrite the equation in this form. V is equal to N over C. Then I can substitute V of H3PO4 is equal to, the number of moles is 0.167 for H3PO4, divided by the concentration was given to be, was it 0.1? I can't remember. Let me check. It was 1.25. So divide by 1.25. What do we get? Okay, I'm getting
So
0.133.
we get So isn't it zero come? Oh yeah, yeah.
That's the same one.
Decimeters
Decimeters
cubed.
cubed, right?
Yes, sir.
Yes. Okay. So that's the volume of the acid. The acid was in aqueous. AQ means aqueous. It's not a gas, it's just a solution of whatever thing that you have plus water. So solution, let me just call it solution in water. That is basically the meaning of AQ. So we can never use this equation. Some people really jump to using this one, but once again, that's only for gases. Okay. So the last question, calculate percentage yield. Percentage yield of carbon dioxide if 4 decimeter cubed of carbon dioxide was formed at STP. And this is always the case for percentage yield. If you write the formula down, it's not given in the formula sheet. I don't know if you remember what it says though. If you don't remember, it's fine. You'll just remember it from now on. Do you remember it or not?
So it's the theoretical over the actual.
It's actually the actual.
Oh, the actual over the theoretical.
Good. So actual,
31st, 31st.
yeah, divide by theoretical. Okay. Times 100. Then which one is always given? Actual or theoretical?
So the theoretical one, wait. So the actual.
The actual is the one that is always given.
Wait, so the theoretical is given, you have to calculate the actual.
No? I thought if I ask you again, maybe you'll change your mind. But you were right the first time. The theoretical,
Oh,
like the word theoretical, it means you have to use theory, which is what we are doing. So we need to calculate the theoretical one using theory. The actual one is the one that they found by performing the actual experiment. Does it make sense?
yes, sir.
Yes, so the actual is always given. Always given. And it's always smaller. If you find that it's not smaller, then it means you are making a mistake in your calculation. It's always given and it's always smaller. We'll see that when we find the theoretical one. But to find the theoretical one, once again, it's the ratio. Nothing new. Um, Nothing like confusing. It's always the same kind of idea. So let's go and see what we need to do. We need to find the theoretical yield, which is nothing but the amount, in this case of volume, the volume of CO2 that was produced in this reaction. So you can see it's just basically a standard question for stoichiometry. If we go back to the reaction, okay, I'm not sure. Okay, there it is. You can see CO3 is one of the products and it's a gas. So that's a good thing. So we need to, at the end of the day, we need to use this equation to find the volume. But I can now use CaCO3 to find the number of moles of that gas by using the ratio. From there, I can use the number of moles equal to V over Vm to find the volume of CO3. And that will be the theoretical value. Make sense?
Yes, sir.
Yes. Once again, this will come back in grade 11. That's why I'm really emphasizing on this. Everything else, or most of the things that you do in grade 10, they won't really come back the way they are in grade 11. But this one will come back the exact way it is. Exactly the way it is in grade 11 and 12. Okay, so let's see what you need to do. this is question 8.4. This one was still part of 8.3, sorry. So 8.4, percentage yield, we know the formula now, but the first thing we need to do is to find the number of moles using the ratio. And the ratio is 3:3 after balancing. And the number of moles of CaCO3, you might remember that is 0.25. So that's what I'm going to write here. 0.25 is to N. Then I cross multiply. I see that we are multiplying by 3 all the time. And those 3's will eventually go and cancel. So I can just go and say that the final number of moles of CO2 is just going to be 0.25 moles. You can do the cancelling out and you'll see that. But this you have to show in the exam, otherwise you lose all the marks. The
Yes, sir.
ratios, yes. If there's anything you are thinking about when you go to a stoichiometric question, it's the ratios. Just after you find the number of moles of one of the things. Okay, then I can go to the N equal to V over Vm formula, because I already know the number of moles. And I know that it's a gas, most importantly. I always write this, so there's no way someone can make a mistake. Therefore, say V into CO2 is equal to 0.25. And because they didn't specify which VM to use, I'm going to use the one that is from the information sheet. And that's 22.4 for VM. Then what do I get?
So, so you get 5.6 decimeters cubed.
Yes, and that's the theoretical yield. Theoretical yield is V of CO2, and that's 5 comma. Said it's 5 comma
5.6 decimeters cubed.
6 decimeter cubed. Good.
6.
All right. So the theoretical yield is 5.6, and we see that it's bigger. Remember, the actual should always be smaller. So we know we are doing a correct thing at this point. Once you get a number that is smaller than 4, then you know immediately that you are making a mistake. I don't know where the mistake could be. It could be that you're using a wrong formula, or it could be that maybe you are using the wrong values, but you definitely are making a mistake if you get a number that is less than 4. But now that it's greater than 4, and another key thing that I check, is it close enough to 4? Because realistically, they try to make them close enough. And I see it's close enough, so I'm confident that I'm not making any mistake. The key to passing is to make sure that you can judge if you are making a mistake or not. And here I'm very convinced that there's no mistake. So I write the formula down: actual yield over theoretical yield. I need to multiply this by 100 at the end. Then the actual yield is always given, and it's always smaller. Divide by the theoretical, which is calculated. I need to multiply this by 100. So what do we get? I'm getting 71.4%. We can make it 2 decimal places and just call it 43.
Yes,
That's,
I also got the same answer.
yes, there we go. That's the percentage yield for CO2. Okay. So that's all about stoichiometry. But I'm sure now you I mean, you are reminded of how it works, are you not?
Yes, sir.
Yes. This is where a lot of marks really come from. If I check this one, it's like 15 plus 11, already sitting at 26. And also this is on stoichiometry plus 14. So we get 15 plus 11 plus 14. You can see this is already a pass mark. 26 plus 14, that's 40. 40 over 100, that's 40%. Already a very good mark just from stoichiometry. Can you see how important it is?
Yes, sir.
Yes, and it's always the same procedure. It's always find number of moles, do the ratio, that's it. And you have this question 7 that we didn't do. This is also on stoichiometry, but it's based on percentage composition, which you said you wanted some reminder about, and empirical formula. And also you can see they have this one question that there's a good recording that we made about the water of hydration. I'm just gonna have you do that one for revision and you just show me what you did. But in terms of percentage composition, I'll show you how it works. It's quite straightforward. And then you said empirical formula, you are confident with that, right? Empirical formula. Can you still hear me? Okay, I think maybe the network went out. Let's check. Are you still able to hear me? No? Okay, I'll stop the recording and maybe let me not stop the recording. Let me just check if I can fix the network. See if we can get back here. Okay. So it says the analysis of a compound made up of elements sodium, sulfur, and oxygen provides the following percentage composition by mass. So when they want you to work out the empirical formula, they will of course give you the percentage composition by mass. And at the end of the day, they'll ask you to find the empirical formula and sometimes also, I'll say most of the time, also the molecular formula. We did a good video on that I will recommend about molecular formula, how to work out molecular formula from empirical formula. Okay, you need to check that out as well. But in this case, I'll just quickly slide through how to do empirical formula effectively. So you're gonna have all these molecules, all these elements in a table like this, or whatever method that you think you're comfortable with. The first thing I'm going to record is the mass, and this mass is from these percentages. So this one is 29.11 grams. So just write the units here under mass: 40.51 grams, 30.38 grams. Then the next thing you want to write is the number of moles, and this one will be in moles. So you just basically take the mass, divide by the molar mass. For sodium, I forgot. Is it 14? No. Let me just check the the periodic table is right here, is 23. Okay, so divide this by 23. Maybe we can just do the whole thing. Why not? Divide by 23. Let's see what we get. And I suggest you write 3 decimal places for this. Then we'll do the same for this one. 40.51 divided by molar mass of sulfur. Let's go ahead and check that one as well. It's 32. So divide this guy by 32. Do the same for oxygen. 30.38 divided by the molar mass of that one is 16. Okay, what do we get for each of these?
So for the first, for the mole for sodium, you get 1,27 moles.
Mm-hmm.
For the mole of sulfur, you also get 1,27 moles.
All right.
So for the mole of oxygen, you get 1,90 moles.
90. Okay, good. Then we divide by the smallest, and the smallest is clearly 1,27. So 1,27 divided by 1,27. That gives us a ratio of 1 here and a ratio of 1 there as well. What about this one?
So that one gives you, wait, I calculated wrong, sir.
Okay, do it again.
So it gives you 1,4, wait, 1,49, no, 1,50. So you have
1,50.
to, yes, sir. So would it be correct if you multiply it by 2 to get like the simplest whole number ratio?
Yes, that's definitely 100% correct. But what I like to say is that you do a little bit of trial and error. Just try all the smaller numbers. If 2 doesn't work out, if 2 doesn't already give you a small, a nice whole number ratio, then try 3, try 4. Once you get to 5 or 6, it's supposed to just work out. But in this case, we see that once we try 2, all throughout, we get a good small number ratio of 2 to 3. So all in all, the empirical formula of this one is, you write this in the order that they were given. So first is sodium, which is 2, sulfur, which is 2, oxygen, which is 3. Okay, that goes for 5 marks, including the definition of empirical formula. I already have 7 marks for this. Okay, simple stuff. Then percentage composition. Let me talk briefly about percentage composition and how it works. So they'll say, okay, looking at this, maybe let me call it something else. If we are looking at Na4, this is just an imaginary compound. And then they say, what is the percentage composition? Find the percentage composition. Do you remember how we solved the empirical formula? They gave us the percentage composition and they want us to find the compound. This is vice versa of what percentage composition wants you to find. They start with the compound and they want you to find the percentages. How you do it is you do this. You go and say, okay, I'm gonna first do sulfur. Maybe let me use the same. Why do I wanna start with sulfur? I'll start with nitrogen, and I'll use the kind of table that I used
So
for.
is it not sodium? It's sodium.
Yeah, sodium. Sorry, yes. I'll use the same kind of table that I used for empirical formula. I'm gonna have the sodium, the sulfur, and the oxygen. And to work out the percentage composition of each of these, I'm just gonna say, okay, how many sodiums do I actually have there? And it's 4. So I'm gonna write the thing is the ratios down, and then I'm gonna say what is the molar mass of the whole thing. So I'll find the molar mass of the whole thing, Na4, S4, O6. And then this is just 4 times 23 plus 4 times 32 plus 6 times 16. Then what do we get?
So why is it 4 times 23? Oh wait,
Uh,
never mind. Never mind.
yeah, that's for nitrogen.
Sir. Oh no, wait, because you keep saying nitrogen, it keeps confusing me.
Oh, sodium,
Sorry.
sorry. Yeah, maybe I'm tired. It's been a long day. I mean, sodium,
Yeah. So you get 316 grams per mole.
316 grams per mole. Good. Then what I need to do is just to say this. Maybe I shouldn't have used the table, but anyways, yeah, the table will confuse you actually, because it doesn't, unlike empirical formula, nothing here depends on the other things. So just do sodium alone here, and then the percentage composition of sodium, I'll call it percentage sodium, is equal to the molar mass of sodium on top divided by the molar mass of the whole thing, Na4 S4 O6. And that's the equation that will work for everything else. Multiply by 100. So for sodium, the molar mass of sodium also multiplied by the molar mass of sodium obviously comes with the 4 as well. So don't forget to multiply this 4 because it's sodium 4. So 4 times 23 alone gives us what?
92.
92. So we're gonna say 92 divided by 316 by 100. This gives you the percentage nitrogen. Do the same for sulfur. It's 4 multiplied by 32, which is the molar mass of sulfur, divided by 316. Multiply this by 100. It gives you the percentage sulfur. Oxygen will do the same. There's 6 of oxygen multiplied by the molar mass of oxygen is 16, divided by 316, which is the molar mass of the whole thing, by 100. So let's see what we get. I'll also calculate. I think I'm a bit quicker with my calculator. So here I get 29.11%. For the second one, I get 40.51. So this one is 40.51%. For the last one, 6 times 16, divide this by 316, I get 30.38. So 30.38%. And that's it. You can see, if I go back to the empirical formula thing, you can see the percentages are exactly the same because that's what percentage composition is about. It should give you the same kind of percentages. even if you are working with a molecular formula instead of empirical formula. So it's all about taking the coefficient, it's not the coefficient, sorry, the subscript for sulfur, it was 4, multiplied by the molar mass of sulfur from the periodic table, divide by the molar mass of the whole compound, which the compound will be given in that case. Okay, so let's see if you can do this one quickly. What is the percentage hydrogen in water? Something simple. You don't need to write anything down. You can just work it out in your calculator.
So you get 11.11%.
Yes, good. Because you're going to take 2, which is a subscript. You multiply that by the molar mass of hydrogen is just 1. Divide by the molar mass of the whole thing is 18. Multiply that by 100 and you get 11.11%. Good. So this means percentage of oxygen will be whatever is remaining from 100 because there's only 2 things. But you can also calculate that 16 over 18 times 100 and it's supposed to give you 88.89, which is exactly what remains from 100 if I take out the hydrogen. So all in all, everything should add up to 100%. Okay, makes
Yes,
sense,
sir.
right? All right, that's good. Let's see the other things that are remaining. We won't do them because I'm thinking we are tired, both of us. But you have things like this ionization energy. We did these things back in like term 1 or 2. I'll recommend the recordings that you need to watch for this. You have the isotopes. You have to remember isotopes and the definition of isotope. That one is always there in the exam, to be honest. Definition of isotope. And the protons, electrons, neutrons. Did you revise these ones? Because they are from term 1. Did you?
Not yet,
Not
sir.
not yet. Okay, you have a lot of work. I don't know if you know. You have a lot of work to do. And you have the cooling and heating curve. This is also from term 1 or 2. A lot of these things, like a lot of marks, let me say a lot of marks are going to come from stoichiometry, but majority of the questions are from term 1 and term 2. Term 3 and 4 have nothing in terms of the questions. So there's things you did a long time ago, but good for us, we have recordings that you can watch to remind yourself. Crucial, crucial, crucial. You can see this one is 12 marks. There's a lot of like singular questions for 1 mark, but if you lose those questions, they add up to a big percentage that you're gonna lose. So just make sure you revise all the theory on that. Question number 2 here was about, I think it's representing chemical change, which is the thing that you did. You know, your Lewis diagrams, your, let's see, which letter represents a mixture, your mixture, homogeneous mixtures, heterogeneous mixtures. What else? Yeah, those kind of things. Chemical change and representing chemical change, I'm thinking here. So yeah. It's also a study guide that summarizes these things nicely, but I want you to actually work on this today so that tomorrow it's just revision. You'll be knowing everything maybe today, and tomorrow you'll just be asking me questions if there's anything you need clarity on. Then the last thing is multiple choice. Here they had 5 questions for multiple choice. Quite easy stuff, I'm thinking. For stoichiometry, only have 1 question, which I think let's just do it for the last thing in the lesson, because we already did stoichiometry today. Let's see if we can answer this one. 1.4. It says, consider the balanced chemical equation below. We have 4 aluminium plus 3 oxygen is aluminium oxide. Which one of the following is the correct number of oxygen atoms required to form 4 moles of aluminium oxide? Which of the following options represent the correct number of oxygen atoms that is required to form 4 moles of aluminum oxide, which is the product? Any idea of what you need to do or the kind of answer you need to pick?
So
Mm-hmm.
can you get like the mole or the limiting factor?
Okay, the limiting factor comes out a lot, and I wanna say it's not something that is important for grade 10. I'm not sure if I might be wrong or what, but that is something that they actually focus on in grade 11. For grade 10, you really never need to use that. You just need to find the number of moles of one of the things. It doesn't matter if it's the limiting or what, because they will always tell you which one is the limiting factor. That they will tell you. So you don't need to really learn how to figure it out. But if you need to, do that. But I'm thinking, as much as I hear you, it's something that can confuse you a lot. Because in this case, you don't really need a limiting factor either. So I'll just say, just forget about that part. If ever they say focus on this thing, they'll say it's completely reacted, and that means it's limiting factor. So yeah, there's no need to find the limiting factor. But anyways, here we don't have the number of moles or any information that will help us to find the number of moles. Oh, or we can say we have them, because they say we need to produce 4 moles of aluminum oxide. So what you need to do is just to do the ratio, right? Oxygen, maybe let me start with aluminum oxide. Al2O3 is 2 oxygen. Then the coefficients are 3 is 2, 2. Then the number of moles of, oh, I'm doing a vice versa now. Before aluminum it's 2, before oxygen is 3. The moles that we have for aluminum oxide is 4. Then I need to find the number of moles of oxygen. I cross multiply. I see that I have 3 times 4 is equal to number of moles of oxygen times 2. Divide both sides by 2. Then the number of moles of oxygen is how much?
6. So it'll be
6.
A.
Yes, you already have the answer, but do you notice that the question itself is not done? You need to then use Avogadro's number, because you are looking for atoms. So I'm gonna say the number of moles is equal to N over Na. Then if I rewrite the equation to find the number of something, that's what I get. Then I substitute, number of moles is 6. Avogadro's number is 6,02 times 10 to the power 23. And that's all we need to, that's where we need to stop in order to pick the answer. And that will be A. Okay. That's how that one should have been done. You can easily choose C, which will be very wrong. But yeah, now you get the idea of what stoichiometry is about. Once again, it's always about ratios, no exception. Okay. Yeah, we'll communicate on WhatsApp if you need anything else. So today we'll just stop here.
Yes, sir.
All right. Thank you and good luck on your exam and all the other remaining exams.
Thank you, sir.
Thank you.
Bye, sir.
Bye bye.